In this example, we are asked to calculate the pH for two separate solutions. In Part A, we are asked to calculate the pH for a 0.0045 molar solution of hydrochloric acid. And in Part B, we are asked to calculate the pH of a 4.8 times 10 to the minus 3 molar solution of barium hydroxide. In each case, the strategy will be first to write the balanced chemical reaction, and in this case, they're acid-base reactions. 2, to write the initial change and final concentration table for the reaction. And then using this table, we can then calculate the pH. The first step is to start with a balanced chemical reaction. Since we know that hydrochloric acid is a strong acid, it will dissociate completely. And so we get HCl dissociates completely to H plus Cl minus. Next, we need to write the initial change and final concentration table. The initial concentration was given in the question, and that is 0.0045 molar. Since we don't start with any H plus or Cl minus, the initial concentrations of those are 0. And since we know that the reaction goes to completion, all of the hydrochloric acid is consumed in the reaction, and so the change in HCl is negative 0.0045 molar. Looking at the balance reaction, we see that 1 mole of HCl produces 1 mole of H plus, and so here the stoichiometry is 1 to 1. So if we're losing 0.0045 molar HCl on the reactant side, then we must gain 0.0045 molar H plus on the product side. For chloride, the stoichiometry is also 1 to 1, and so we have a change of plus 0.0045 molar for that as well. For the final concentration, we simply add up the columns, and we notice that this column adds up to 0, which makes sense because all of the HCl is consumed in the reaction. For H+, we produce 0.0045 molar H+, and for chloride, we also get 0.0045 molar Cl-. Now, in order to calculate the pH, we will need the hydrogen ion concentration. And starting with the equation for pH, we see that pH equals negative log of the H+ concentration, and simply substituting this into the equation here gives us negative log of 0.0045. Plugging that into our calculator, we get 2.346 as the pH. Now, here we see that we have two significant figures in our data, and so we should have two significant figures in our answer. So rounding to 2 decimal places gives us a pH of 2.35 as our final pH. And this again is the two significant figures. Keep in mind that for pH, because it's a logarithm, the significant figures are determined by the number of figures after the decimal point. For part B, we are looking at barium hydroxide. And in this case, barium hydroxide is a strong base, and so this will also dissociate to completion, giving us Ba2 plus and 2 OH minus. You'll notice that here we have a stoichiometric coefficient of 2 in front of the hydroxide, and that's because the chemical formula of barium hydroxide is BaOH2. So we see that in each mole of barium hydroxide, there are 2 moles of hydroxide, and that shows up in the stoichiometric coefficient shown there. Next, we write the ICF table. The initial concentration of barium hydroxide was given as 0.0048 molar. And again, in this case, we did not start with any barium or hydroxide. So the initial concentrations of these are 0. And again, because the reaction goes to completion, we lose all of the barium hydroxide. So the change in BaOH2 is therefore negative 0.0048 molar. For barium, the stoichiometry is 1 to 1. So the change is plus 0.0048 molar. For hydroxide, things are a little bit different because here the stoichiometry is 1 to 2. And so for every mole of barium hydroxide that we lose, we gain 2 moles of hydroxide. And because this is negative 0.0048 molar, then this has to be plus 2 times 0.0048 or 0.0096 molar. Final concentrations, we simply add up the columns again. For barium hydroxide, it's 0 as expected because all of the barium hydroxide is consumed in the reaction. For Ba2+, the final concentration is plus 0.0048, and for hydroxide, the final concentration is plus 0.0096. Now, in order to calculate the pH, we can do this a couple different ways, but the easiest is probably to calculate the pOH first, and we calculate the pOH from the final concentration of hydroxide. So the equation for POH is POH equals negative log of the hydroxide concentration. And we have that, so we'll just substitute that into the equation, giving us a negative log of 0.0096 molar. Plugging that into our calculator gives us a POH of 2.017. Now we can calculate the pH using pH equals 14 minus the POH, and substituting the POH in, we get 14 minus 2.017. Plugging that into our calculator gives us 11.982, and rounding gives us a pH of 11.98.